Hello, in this video we are talking about bond energy and how we can use it to calculate the enthalpy of a reaction. These notes can be found on page 23 through 26 in your book. Chemical bonds form to lower the overall potential energy of a system. So the potential energy of bonded atoms is lower than that of the independent atoms. Whenever we make bonds, it's an electrostatic process because we have an interaction between the two positive nuclei and the negatively charged electrons of the different atoms participating in that bond. Electrostatic processes are always governed by Coulomb's law. So we've seen Coulomb's law a few times in pre-AP and in AP as well. The force of attraction or repulsion in Coulomb's law is directly proportional to the magnitude of the charges. So our Q1 and Q2 would be our two charges, and it's inversely proportional to the radius or the distance between those two charges. Negative electrons of our atoms and the positive nucleus of the other atoms it's trying to bond to attract to one another. Opposite charges attract. But if the two nuclei, the two positively charged nuclei, get too close together, they start to repel each other. So atoms have to find that kind of perfect spot where they have that attraction between electrons and the nucleus while minimizing the repulsion between the two separate nuclei. That optimum distance between the two atoms is the bond length. That's where we have the lowest energy state because we have maximized our attractive electrostatic forces and we've minimized the repulsive forces in the atom between the two atoms that are trying to bond to each other. So as we look at this graph here, we see our radius on the x-axis and potential energy on the y. When that radius is really small up in this top part of the graph, there are very large repulsive forces. Those repulsive forces are not favorable. That is no good there. So we have a really high potential energy. But as we drag our atoms a little bit further apart, we reach the point of lowest potential energy on this graph. That point of lowest potential energy is where we have the most stable state of the compound that we are forming here. That is where we have maximized the attractive forces and minimized the repulsive forces. As we continue to move those atoms further and further apart, that potential energy is going to increase again because we are decreasing the attractive forces as the atoms get further apart. We're going to be looking at the energies involved in breaking chemical bonds and forming new chemical bonds. When we break chemical bonds, we have to input energy to overcome the attractive forces. It's an endothermic process. But when we form new bonds, energy is going to be released as that new attraction is formed. Energy is released with the new attraction because that's what's going to take us to the lowest potential energy process. The difference between the amount of energy we need to break the bonds and the amount of energy that comes out whenever we make new bonds determines if the overall process is endo or exothermic. Difference in energy that determines whether it's endo or exothermic, that's the exact same thing as the enthalpy change for our reaction or our delta H reaction. So using bond energies is yet another way that we can determine the enthalpy change of a reaction by looking at the bonds that are broken. Again, that'll be an endothermic process, and the bonds that are formed. The total enthalpy change, or your delta H, would be negative exothermic or positive endothermic, depending on the magnitude of both of those processes. Does it take more energy to break the bonds, or was more released whenever the new bonds were formed? So again, endothermic processes are going to have a positive delta H. Breaking a chemical bond is always endothermic. So ending a bond is endothermic. Exothermic is going to be a negative delta H. That's going to be forming a chemical bond. Forming a chemical bond is always going to be exothermic because it puts our new chemical in a more stable state at a lower potential energy. So to get to a lower potential energy, energy had to be released from the system. So let's look a little more in depth at how this process works. In this picture here, we see our increasing enthalpy is going up. We are starting with our reactants, which are the CH4 and the Cl2. We're going to have to break the bonds in methane and break the bonds in chlorine in order for our atoms be able to rearrange and form our new products. Breaking bonds is an endothermic process, so it's going to take energy to break one of these C to H bonds and one of these C to L bonds to form those intermediary products that we see there. Once we've broken those bonds, we're able to make our new bonds. Making new bonds is an exothermic process, so we're going to have to form the new carbon to chlorine bond and the new hydrogen to chlorine bond. Energy is going to be released whenever those new bonds are formed. Well, we can see here that the amount of energy that was required to break our bonds is less than the amount of energy that was released when our new bonds are formed. The difference in between those two energies is the heat of reaction. So that heat of reaction, or enthalpy of reaction, again is the difference between those two that we see right here. Because it took more energy was released when we formed those new bonds, our overall delta H of reaction is going to be negative. So using this relationship, we actually have a formula, a way to calculate using the bond energies, the actual delta H of any given reaction. This equation is not on your formula sheet, so you will need to memorize that. The overall heat of reaction is the bonds broken, so the sum of all of the bond energies of the broken bonds minus the sum of all of the bond energies for the bonds that are formed. Both of these ways mean exactly the same thing. Bonds that are broken are the bonds that are in the reactants. Bonds that are formed are all the bonds that are in the products. So again, we would use the bond energies for those. Again, this is not on your formula chart, so you will need to memorize this. One thing that might help you remember this is that using bond energy is going to be backwards from what we see on the formula chart. We have that big mama equation on the formula chart, which is the heat of formation of our products minus the heat of formation of our reactants. Again, bonds is going to be backwards. It's actually reactants minus our products. Well, we have to be able to determine which bonds are being broken and which bonds are being formed. You have to draw the Lewis dot structures of those compounds in order to determine that. Once you know which bonds are being broken and which bonds are being formed, you need the bond energies for each of those bonds. Those are either going to be given to you in the problem or you'll be asked to look at a table. So the amount of bond energy that it takes to break or make what's released when you make a bond depends on the type of bond that it is. Double and triple bonds are going to be stronger than single bonds because they have a greater number of electrons that are being shared. So Coulombic attractions from the shared electrons to the nuclei are going to be stronger. It's going to take more energy to break it, or more energy would be released. Shorter bonds are also going to be stronger as well. So we can have shorter bonds whenever we have those double and triple bonds. Those will also be shorter. We also have shorter bonds when our atoms are smaller. So like two hydrogen atoms are really, really small. They can get really, really close together. Whereas two chlorine atoms, a little bit larger, their radius is going to be bigger. They can't get as close together. That bond energy is going to be a little bit weaker due to that larger distance between them. So we can see that relationship here. Our triple bond is the strongest. It is also the shortest. The double bond is a little bit longer, also a little bit weaker. It's not going to take as much energy to break. The single bond is the longest bond, and it also has the lowest bond strength. That means it's going to take the least amount of energy to break it. So it takes 347 kilojoules per mole of those carbon-to-carbon single bonds to break them, and 347 kilojoules of energy will be released when we form that new bond. So on the top of page 25, you have a table of your bond energies that you'll need to do on some of the practice and examples that we'll be going through there. Only big thing of note on this bond energy table is that carbon to oxygen double bond. Whenever we have that carbon to oxygen double bond, you see that asterisk there. Whenever it's a carbon to oxygen double bond and carbon dioxide, it's actually going to have a different value than any other molecule. In carbon dioxide, that would be 799. So that's what that asterisk is. So let's check out an example of this together. We want to use the bond energies from that table you just saw on the top of page 25 to estimate the heat of combustion for the following reaction. We want to know if it's endothermic or exothermic. Well, that heat of combustion, that combustion is just there to say that it's the specific reaction. So if we're looking for heat of combustion, we're really just looking for the heat of the overall reaction. So we are using the bond energies to calculate this delta H, which means that it's going to be bonds broken minus bonds formed, which is alpha order, or reactant bonds minus product bonds, which is the backwards order of what's on the formula chart. So to figure out those bond energies that we're going to be breaking in our reactants and the bond energies that we're going to be formed in the products, we're going to have to draw the Lewis structures. So when we look at CH4, we know hydrogen can only have 2 electrons. It has to be on the outside of an atom, so carbon's going to be our central atom, our 4 hydrogens around it. Carbon has 4 valence electrons. Each hydrogen has 1 valence electron. Everyone wants to get a full shell, so we're going to share electrons, connect the dots there. Each hydrogen has 2 electrons, which is all it needs to get that full valence shell, whereas carbon has 8 electrons, which is what it needs for its full valence shell. Our other reactant is our O2, and we have 2 of these O2 molecules. Each of the oxygens has 6 valence electrons, which means for them both to get a full shell, they're going to have a double bond between them. Now each oxygen has 4 electrons all to itself, plus 4 that it is sharing in the double bond for a total of 8. Let's take a look at our products. First product is carbon dioxide. Carbon's going to be our central atom. Carbon tends to form 4 bonds because those 4 electrons that we have there, whereas oxygen has 2 unpaired electrons, it tends to form 2 bonds. So we end up with a double bond between carbon and oxygen on both sides there. Our only other product is water, and we have 2 of them. So oxygen must be on the outside. It will be single bonded to oxygen. Oxygen will have 4 of its own and the 4 that it's sharing between the 2 hydrogens. If you are adept at drawing Lewis structures, you do not need to worry about including all of those extra lone pairs here. Now that we have our Lewis structures, we can determine which bonds we need to break and which bonds we need to form. Again, the bonds that we're breaking are on the reactant side. I have to break all 4 of these carbon to hydrogen bonds plus this O to O double bond, and remember I have 2 of those. Then I need the total amount of bonds that are formed. I am forming 2 carbon to oxygen double bonds, so there's 1 of them, there's 2 of them. And then in my water, I'm forming 2 O to H bonds, but I have 2 waters, so in total, we're actually forming 4 O to H bonds. So now we just simply need to go find all these bond energy values in the table above on page 25 and do this calculation. So from the table we find 413 for that C to H bond, 495 for O to O double bond, 799 for that C to O double bond, it's the CO2 asterisk one that we need to use there, and 467 for the O to H. When we put this all into the calculator, we should end up calculating a negative 824, keeping 3 sig figs from those bond energies, kilojoules per mole reaction. We also wanted to know if this would be an endo or exothermic process. Well, it's going to be exothermic because that delta H is negative. That means that more energy was released when I formed those new product bonds than what I needed to break the reactant bonds. There's a couple more bond energy practice on page 26 that we'll be working on in class next time.